Okay, so now the question is, are there Z1, Z2 that give us absolute value of Z1 plus absolute value of Z2 over 2 equal to 1 over root? So that's the question. Can I find an example that gives you the equality, or can I get at least close to 1 over root 2? So that's the next thing I need to check. So when, as I said here for AMGM, the equality holds when all of these values are the same. So I need to be looking for the equality case. So I need absolute value of Z1 equals absolute value of Z2. So that's what I need. And if they are the same, that means I need both of these to be 1 over root 2. If the average is 1 over root 2, which means absolute value of root 2 Z1 and absolute value of root 2 Z2 are both 1. Okay, but one can, so I'm looking for a quadratic polynomial whose the roots are, you can think about these roots, are of absolute value of 1. So one way would be to look at cubic roots. So if you have x cubed minus 1 equals 0, that gives you x squared plus x plus 1 equals 0, assuming that x is not 1. So this might be a good idea, good example. So then you are going to substitute that with root 2 times say t. Then you're going to get this polynomial, 2t squared root 2t plus 1. And in fact, the coefficients of that do satisfy the inequalities that we are looking for. Less than 2, and that's less than or equal to 2. So they do satisfy those inequalities. So that's nice, because that way I can actually get my intended inequality. And that would be our example. Now moving on to the cubic polynomials. I'm going to do the same thing and see what happens. So I have b3x cubed, b2x squared, b1x, and then b0 equals 0. Then I'll take the average of all of them. I guess there's only 3. And that's greater than or equal to cube root of their product, which is cube root of b0 over b3, which is greater than or equal to 1/3 cube root of that. And then we can find an example by doing essentially the same thing. So we want absolute value of z1, z2, and z3 all to be 1 over cube root of 3, which means absolute value of cube root of 3 z1, cube root of 3 z2, cube root of 3 z3, they're all 1. So you could think about a cubic that all of the roots are roots of unity. So one example would be x cubed plus x squared plus x plus 1. And then the roots of that would be cube root of 3 zi. So those are going to be the roots. Then you take that, plug it into the equation, you get 3z cubed plus cube root of 3 squared z squared plus cube root of 3 z plus 1. So that would be your equation. So that seems like we found the solution now. So now we're going to write down the solution. Okay, so I'll put the answer here. Now, we can tell what the answer should be. It's 1 over 2019 root of 2019. So we prove the answer is 1 over 2019 root of 2019. Okay, So what I'm going to do is I'm going to, just for simplicity, because I don't want to keep writing down 2019, I'm going to call, just like set n to be 2019 so I don't have to repeat that. So for simplicity, let n be 2019 through of 2019. Note that absolute value of z1 all the way to absolute value of zn over n is greater than or equal to nth root of their product, which is nth root of, so it's a constant term divided by the leading coefficient, which is greater than or equal to 1 over nth root of n. So that proves the inequality does hold. Now, let p of z be this polynomial. Let, or I guess q of z, I'm going to use a different variable for the name of the polynomial, or q of x. So 1 plus nth root of n plus x plus nth root of n squared x squared all the way to n x to the power of n. Then the coefficient of q satisfy, okay, so the first coefficient is at least 1. The next coefficient is more than 1. The next coefficient is more than that, and so on. So they satisfy the property that they gave us. Furthermore, q of x, this is a geometric sum. So it is 1 first term minus nth root of n x to the power of n plus 1 divided by 1 minus common ratio, nth root of n times x. So that's the that's q of x. So each zi satisfies 1 equals nth root of n zi to the power of n plus 1, which means absolute value of nth root of n zi is in fact 1, which means absolute value of zi is nth root of n, 1 over that. That means if I add up all of the zi's, absolute value of zi's, and divide by n, I get n times absolute value of z1 over n, which is 1 over nth root of n. And this is exactly what I was looking for. So I came up with one example that does give me 1 over nth root of n, and I showed every other example gives you something larger than that. So that completes the proof.